Good morning, everybody. So, last class we began discussing the simplified neuron models, especially the low-dimensional or two-variable neuron models. So we looked at Fujinovo model, Morris-Descartes model, and also this INAPK, right, neuron model. And we saw that they all have some common features. So now in this class we'll explore if you can kind of combine all those common features and create some kind of a standard or a canonical model. Okay, so that was proposed by a guy called Eugene Mizukovic. So we'll call them Mizukovic neuron models. So they have two variables. So we'll define that very shortly. Then after that we'll start looking at single variable neuron models. Even these can be quite powerful, quite expressive. So we'll start with quadratic integrated fire neuron model, which has only one variable. Then leaky integrated fire neuron model, one variable again. The dynamic neuron model, one variable. So these two, the quadratic integrated fire and leaky integrated fire, are spiking neuron models. So they produce some kind of spikes. Whereas the dynamic neuron model, the dynamic binary neuron model, it doesn't produce spikes. It just has bistability, and it can be in a high state or a low state. Then we'll even simplify further and come up with the static neuron model, which is what is which is what is used in artificial neural networks, right? So basically, what we are doing is we are trying to simplify from started with very complex, very detailed biologically inspired neuron models and progressively simplifying them and arriving at the simplest possible neuron model, which is what people use in artificial neural networks. Okay, so if you'll see what we have done, right, with the three models that we discussed in the last class. So if you start with the Fujinovo, right, you have this N-shaped nonlinearity, and then the W null plane is like this. All right. So for zero current, you just have this kind of excitability, where if you start from here, you make this long circuit and come back. Right, but if you lift this up, right, if you lift this up, it will intersect, right, the middle branch, and you have oscillations. Okay, so basically for IA less than some threshold, you have excitability, okay, and no oscillations, and for IA greater than some threshold, okay, oscillation. So this is what we saw in Fujinovo. And even if you look at Morris-Descartes, essentially same thing. So only thing is in this case, again you have a kind of N-shaped nonlinearity for the Venal line. The other null line is not a straight line, but it was looking like a sigmoid. Right, but here also again you have three cases: sigmoid intersecting it here, sigmoid intersecting it here, right, and so on. We also had third case, but the main most interesting thing is that how do you produce oscillations? How do you produce the spikes? Right, these action potentials. Okay, so if we saw that if this intersection point is to the left of, so this point is the minimum point of the N-shaped null plane, or is most important thing. If the intersection point is to the left of that, that is in the first branch, right, you just have excitability. And if it moves to the right side of it, right, then there is oscillations. Okay, and so you have similar behaviors even in case of INAPK model. Right, here also you had some kind of this null plane and then a sigmoid. Okay, and so again here also you can say that if IA is less than some threshold, right, excitable, and IA greater than some threshold, oscillations. You can say the same thing about an APK, and even if you look at Hodgkin-Huxley, right, this feature is common, right, to all three, and even the fourth one, even the first one, which is Hodgkin-Huxley. And the secret is the main place of action, right, is this part, whether the W null line intersects the V null line to the left of this point or to the right of this point. Okay, whole thing is happening in this small zone, right? So, and it is showing these are two main behaviors, because we also discussed that a neuron has basically two states: the resting state and the spiking state or exhortatory state, right? And that you get by increasing your current beyond the threshold value. So these features, right, can be produced using a much simpler model and some kind of a canonical model, like a standard model, right? It doesn't have to show anything else. If it shows something else, that's fine. But can you construct a simplest possible model which has these features? So that is what motivated the creation of this two-dimensional model, which is proposed by Mizukovic, right? Therefore, it is sometimes also called Mizukovic model. So just this is again summary of what I just said. So the previous models have these common features. There's a resting state for I equal to 0, and there it is excitable, right? And so a sufficiently large current I, it shows limit cycles or oscillations or spikes, you can call it whatever. And it has two null lines. The n-shaped null line for V, right? And second null line is either linear or sigmoidal. Okay, so that is a common thing. And the intersection between null line and second null line near the U shape, the minimum point of the V null line, that plays a crucial role in the dynamics. Okay, so like I said, so this is the part which is most important, and the intersection around this part, right? That's most important. So can we capture this in the simplest possible model? So how do you do that? So for doing that, it is enough, since the minimum point is more important. This is not that important. We can just take a function which is like this, right? And right, and for second one case, it can just be a straight line. Okay, so what kind of functions will give you this? So this, if it is enough, if it is a quadratic function, because in Fujinogumo we used a cubic function, and Morris-Lecar and INAPK, the Venal line formula is actually quite complicated. Its shape looks like it has an N shape, right? Which you can also approximate using a cubic function. But its actual expression, if you go back and look at your notes, it's actually quite complicated, right? And whereas we are trying to simplify even further, even simpler than the cubic, because if this is the only thing that's important, quadratic is enough. And this double null plane can be just linear. So can we construct a model which has just a quadratic null plane for V, the linear null plane for W, right? And make it produce the same kinds of behavior? This is the question. So to that end, so you can approximate a V null plane using something like this. So here notice that instead of W notation, we are using a new variable U notation, which is what is used in the Mizukovic neuron model. So we'll stick with that. So the quadratic part is given by this formula, right? And the linear null line for the second one, variable U, is given by this one. So the variables are U and V. And therefore the corresponding dynamics, right, for this one will be something like take U to the right side, so you have minus U. Null line will be 0 equal to minus U plus all this stuff. So that gives you the first equation, this one. And similarly, if you take U to the right side, you get minus U here. And if you write the derivative on the left side, that gives you the second equation. Okay, so these are similar, right, in overall nature to the Fujinogumo and Morris-Lecar and all that, right? But let us see how it works. So now if you take two null lines like this, there's a quadratic function, and then there is a linear function, right? So this is the U dimension, this is the V dimension. So, so if you look at these expressions, right, this expression, so this equal to 0 is the V null line. But if you go above that, since U appears in like as a negative term, if you go above that, V dot becomes negative, right? So here V dot is negative. Therefore, here also V dot is negative. So therefore, contrarily, if you go below this, V dot is positive and V dot is positive. So here also you are dividing the entire phase plane into 4 regions. So now, so this is the V null line, and this is the U null line. So similarly, if you take the u-null-line, so that is this equal to 0 is u-null-line. If you again go above above this curve, this straight line, since u appears with a minus sign, it will be negative. So above this, u dot is negative. Okay, and therefore here also u dot is negative. Whereas below the line, u dot is positive, u dot is positive. So you can see that just like before, right? If you are here, v dot is negative, and also here also you can say that u dynamic is somewhat smaller in magnitude. The signs keep changing, but it's smaller in magnitude compared to v dot. So here the flow is to the left and v dot is positive. Here also flow is left but downwards. So here flow is to the right and down. Okay, and here flow is to the right and above. Okay, so some kind of circulation is going on here also. But again, like last time, you can show that if it is to the left of this minimum, it will be a stable point, but like maybe a stable focus. And if it is right of this, it becomes unstable. And that's where you'll get a limit set. So it's that behavior is, that's where you can get oscillation, but things are more complicated here. I'll talk about that. But one thing you'll notice here, you can immediately notice that there is a problem with this formulation, which is if you are here, v dot is positive, u dot is also positive. And you can, there's a danger of simply going off to infinity like this. The v dot is positive. And you may never come back. So that means you don't have oscillation, there's no spikes, right? Why doesn't this happen in case of Fujinogumo, right? Because in Fujinogumo, we had the n-shaped nonlinearity. So if you go off to the right side, because here v dot is positive, once you hit the null line again at a later point, right? Since here v dot is 0, you cannot cross it. If you cross it, you'll be pushed back here, right? And then after that, you climb up. So there is some kind of a limiting factor because the null line also goes further beyond and again comes down because it's a cubic nonlinearity. When you have a quadratic nonlinearity, the good thing is it is of a lesser degree in terms of nonlinearity. But point is, when you go out to infinity like this, there's nothing that stops you. Okay, so it is bad. The model is bad. You need to do something about this. And not only that, you can show that it goes off to infinity. Not only that, it goes off to infinity in a finite time. So how do we see that? So for that, so basically you have v dot is equal to a quadratic term, right? And u dot is equal to and a linear term. So this is what you have in this model. So to simplify this, let me take a simple version of this. Let us forget that u dot influences v dot, right? There's a minus u term here. So just take this simple equation. V dot is equal to say 1 plus v. Okay, so 1 plus v square. So the quadratic term expression I'm simplifying to like really something simple. Just a constant term plus positive constant term plus v square. Even that I'm taking as 1 without loss of generality. So now if I have a differential equation like this, v dot is equal to 1 plus v square. How does v vary in this case? So you can take it as dv by 1 plus v square is equal to dt. So if you integrate this, the integral of 1 by 1 plus v square, right, is nothing but tan inverse of v is equal to some t plus c. Okay, so let us assume that v starts from 0, right? So I'll just take it as t. So then v is equal to tan t. Okay, it varies as a tan function of time. So that means if you plot it, right, it will go off to infinity at pi by 2.
Yeah, so the last line is not visible actually. The last line when you are writing, no? So
okay,
that is coming. Yeah.
So I'll try not to go to the bottom.
Right. Yes.
Okay, so basically what I'm saying is, so can you see this point, dv by 1 plus v square?
Yes, that is visible. Only
Okay,
the
so
tan thing. Yeah. Only
so tan inverse is visible.
That is visible.
Okay,
Below
so
that.
yeah. So basically tan inverse of v is equal to t. So v is equal to tan t. Okay, so basically what I'm trying to say is when you have a quadratic nonlinearity, the V variation will take a tan form. So therefore it can reach infinity in a finite time. Okay, when t equal to pi by 2, it will reach infinity. Whereas if you take a linear expression, just 1 plus v, right, you have v by dv by 1 plus v on left side, so you get a log function. If you take log to the right side, you get an exponential. So in that case, v simply increases as exponentially with time, but still it takes infinite time to reach infinity. But but if you take even if you take a quadratic nonlinearity, which is, I mean, the smallest nonlinearity that's possible, v already reaches infinity in finite time. So okay, so it not only reaches infinity, it reaches it in finite time, right? So we need something to stop that, because you cannot have voltage going to infinity. It doesn't make any sense. So to take care of that, what people have done, what in this model, there is a separate resetting term. That is, V is reset upon reaching a peak value. So once it reaches some kind of a peak value, like I'll call this VP, right? It is just reset back to something, I don't know, some value like that, right? And so that is it reset to the V reset value, and U is also reset, but U is not reset to a value; it is updated. Okay, so V is simply reset to V is equal to V reset, and U becomes U plus U reset. So U is update, so it is actually an assignment. It an assignment, right? And so it is just pushed back, right? And so this is the complete system. And so to simplify these equations, these expressions can be simplified further. All this stuff, the notation can be simplified, make more general. So dv by dt is equal to the current I plus v square, the correct nonlinearity, minus u, and du by dt is a into bv minus u. Okay, so this is linear. So this is the canonical form of this equation, this model. And here the resetting voltage is 1. So v is greater than 1, right? V is reset to c, and u is reset to u plus d. Okay, so there you can see that there are totally 4 parameters, A, B, C, and D. And already here the reset voltage, the voltage at which it is reset is being taken as 1. Right, so there are totally 4 constants or 4 parameters. And depending upon the choice of the parameters, even the simple system gives you very rich dynamics. And Mizukovic showed that since you are varying the parameters, you can show all these rich kinds of spiking behaviors. And in fact, these kinds of behaviors are really seen in real neurons, right? And for example, take this. This is called tonic spiking. So tonic, in engineering terms, you can say it is like steady state. Okay, what that means is, so this trace below is the input current. Input current, if you give a step current for certain values of ABCD, and it's not shown here. So we'll do a tutorial class on that and to show you all that. So when you give a step current to this particular neuron model, that means the same model with particular values of ABCD will show some initial transient spiking. After that, it produces spiking with a uniform rate, uniform frequency. So that kind of a steady state spiking with a uniform frequency is called tonic spiking. So for some parameters, you can show that. So similarly, the same neuron model can also show what is called phasic spiking. So phasic, again, to translate into engineering terms, this is neuroscience term, is simply transient. Okay, transient means it will spike briefly and stop. So in this case, it's showing one spike and it's stopping. Now, bursting is a different kind of neuronal behavior. A lot of neurons show this behavior, which is it produces spikes, right? But produces a high frequency spike within a short duration. And then there is a pause after that. Again, high frequency spikes within a short duration and pause after that. So this is a burst. Okay, so the overall frequency might not be very high, but within the burst, it can reach a couple of 100 hertz and things like that. So this kind of behavior is called bursting. So for some other parameters, the same canonical model can even show bursting. Right? This is tonic bursting, that is repeated bursting. And for some other parameters, same neuron model can show phasic bursting, which is one burst in the beginning, and after that there is total silence. Or it can show mixed modes for some other parameters, that is initial bursting, which is like phasic bursting, followed by tonic spiking. Okay, so there's a mixed mode. So like that, he shows how the same canonical model can show like in a wide variety of behaviors. For example, here it shows bistability. That means, so normally, so in this case, when you give a constant current, as long as the current is presented, it keeps on spiking at a uniform rate. In this case, again, for a different set of parameters, if you give an initial pulse, right, it starts firing and keeps on firing after that. It's only a pulse, it's not a DC current. And then if you give a pulse again, it stops firing. It's okay, some kind of a button. You press the button, the tape recorder plays, and you press the button again, it stops playing. So what is quite surprising is a simple model like this. I mean, this looks like nothing. It's like a quadratic nonlinearity, and so only the first equation is nonlinear. Even that is consists of only quadratic nonlinearity. Second equation is even linear. But point is, this is slightly deceptive because although the equations are not very nonlinear, the resetting step, which is actually this is where the magic sauce is. Right, the resetting step makes the whole system highly nonlinear. And this combination seems to somehow work the magic and give you a wide variety of behaviors seen in real neurons. So this is where we should understand that you don't need very complex models to produce complex behaviors. Even very simple model, but properly designed, right? You need to have brains to design those kinds of models. They can produce very complex behaviors. Okay, so that is one thing. Now we'll show all these behaviors in a tutorial class, maybe Friday this week, right? So I'll move on to the next model. The next model is even simpler. We can easily theoretically analyze it and understand why it behaves like this. It is again on the same lines, but just imagine that the second equation is not there in the previous system, and that model is called a quadratic integrate and fire neuron model. So the integrate and fire neuron is actually a whole class of models. So basically what happens in this is there's one equation where the voltage gets charged up, right? And once it is charged to a certain value, right? And if it crosses the threshold, you just reset it, which is what we have done in the previous model also. So that process is called integrate and fire, right? You build up V, and then once it reaches the threshold, reset it. So then the neuron fires. So in this model, the voltage equation is dV by dt is equal to I plus V square. I is the external current, right? And the resetting is like this. If V is greater than V peak, then V is just reset to V reset. Okay, so these two are parameters. So let us see how it works. To understand this, let us just plot the expression I plus. So the y-axis is v dot. Actually, sorry, y-axis is v dot. And x-axis is v. So I'm plotting v dot versus v. Just ignore this. Okay, and so why is it? So it is v dot is positive in this part, right, and negative in this part. So why is that? Because vi is I plus v square. So if I is negative, right, you get a situation like this. And you can see that these two are the roots of this, and the roots are at plus or minus square root of minus psi, right? Because this goes to 0. And so just let us see what happens here. V dot is so if you go above this, right? So this is on this V dot is 0. So if you go above this curve, right, V dot is positive, and below that V dot is negative. So if sorry, if V is greater than this, right, V dot is positive, so it will keep on going. It will keep going to infinity, right? If similarly, if on this side also V increases, so V dot is positive here. On this side, V dot is negative, right? So because of this, what happens is, okay, so within this interval, V dot is negative, right? And outside this interval, V dot is positive, right? So if you are on this side, V dot increases, V dot is positive, so V increases. If you are in this interval between this is minus root of minus I, and this is plus root of minus I. So if V is between these two, it will decrease because V dot is negative. Beyond this, it will increase. So what is happening is this is like a stable point, and in fact this is a resting state. Okay, but if for whatever reason, if you can kick V right beyond this point, and it will go off to infinity. So if there's nothing that stops it, it will go off to infinity. And therefore, what we do is, if it reaches some value, which we'll call V peak, right? We just reset it, and you just imagine that resetting happens, something like this. And let's say we reset to this point, and I'll call that V reset. Right. So then what happens? It will creep back. So once it reaches here, I'm quickly putting it back here, and it will creep back to this point. And once it reaches, it stay there. So this point is like resting state. I'll call this V rest. And if I kick V from here, if I don't kick it beyond this point, it will slide back here. Okay, but if I kick V beyond this point, it will go out infinity. So this value is like V threshold. So you can see that all these features are very similar to what we have seen in case of Fujinogumo. We had all these things in Fujinogumo. So this is the threshold value A, right? If it is within this part, it will come back. If it is beyond that, also it will come back. If it goes beyond, it goes away. And once it reaches here, it is reset in some sense, and goes and comes back all the way here. Okay, so it goes beyond and then kind of comes back. So those features are all brought here in this very simple model, which is a single variable model. So here also, just by varying, so you have parameters like vrest. Vrest is not is implied in this equation, but the V reset is a parameter. V peak is also a parameter, right? And I is the external input. So depending upon the choice of these parameters, we get very interesting behaviors. So like I said, if I is negative, so right, V dot is 0 at two values, at plus or minus root of minus I, right? So the left root I'm calling it V, the V rest, and right one I'm calling the V threshold or V thresh. So okay, we described all this. So case one is what we just described, right? With I negative, this curve goes below this axis. So there will be between these two, V dot is negative. So this is the resting state, and this point you imagine is the V reset point. This is the threshold point, and this is a reset process. Right? It's not that it is actually going in this space, because actually there's only one variable, which is V. So once it reaches here, it is quickly reset back to this point. So so this on the right side, you see a simulation result. You start with initial condition at about at 3 or something like that. So once you cross above that, it's trying to go up to infinity, but the V thresh is 11, right? Once it goes at just sharply reset, so it's just falling. So the rise is somewhat smooth, but although quite sharp, but the fall is abrupt, okay, because it's just resetting it. So it goes to this point, and that is this point. So we reset. After that, it slowly creeps back to this point and comes back to this is V rest. Okay, so like that, it can produce an action potential, but in this case, for I negative, if you give it a kick, right? It'll and kick is sufficient. The kick is sufficiently high that it can be pushed beyond this threshold value. It'll just show a single spike and stop. This is like the excitability mode that you saw in excitability that you saw in case of Fujinogo model for zero current. So now we'll show a different result. That is, V reset in the previous case was to the left of the V rest. Okay, so that means it's less than V rest. But suppose V reset is beyond V threshold. Okay, you have something interesting, right? So again, this point is still like a resting state because if you from left and right, you come back to the same point. But for whatever reason, if you get kicked beyond this V reset, right, you go beyond this. This is my V threshold. Okay, and this point is V reset. So once you go to this point, you get reset here immediately, and again you climb up here slowly, somewhat slowly, and again you get reset here, climb up here. So it will keep on spiking forever. So you see, so this repeated return from here to here, right? So that's what you are seeing in this plot on the right side. It goes to this level and comes back to this point, and it keeps on doing it. It will never go all the way here. Okay, but if you while it is spiking like this, if you give it a sufficiently sharp or a strong negative current pulse, right, and if you can push it beyond this value, right, then after that it will creep back to this resting state and stop there. So in this case, it has two stable states. One stable state is just a point, which is the resting state. Other stable state is the repeated spiking, right, which is a kind of an oscillatory state. So this shows bistability. Then something interesting happens when so in this case also current is negative, but only thing is we change the V reset value. In the next case, you make current positive. So here when current is positive, and again the same thing, right, V reset. So the resetting is happening here. This is the V peak value. So when you reset here, it will go to V reset and climbs back again. So the thing is, this neuron will keep on firing. All right, there's nothing. You don't have to give any pulse, nothing. It just keeps on firing forever. And something interesting happens. So we have already seen this, right? But in this case itself, so just make a. So case 3, we have seen that if I is positive, that it keeps on spiking. Sorry, it increases smoothly and falls sharply and so on. Okay, but imagine what happens when I is positive but only slightly positive. Okay, I is 0 is less than I, but it's less than 1. It's a small number. Okay, what happens in this case? So you can notice that when these two are actually touching, okay, so then you have a 0, right? And so suppose they are actually touching, so then I is 0. Okay, if I is 0, they're actually touching, right? So you move towards it. And once you reach this point, V dot is 0, right? You stop there. Okay. But whereas I is non-zero, but a very small number, what happens is at this point, V dot will be actually very small. So therefore, it moves, so it slows down once it comes to this point, right? And goes beyond this. So then what happens is if you go to some value V peak here and you get reset to this, when it comes beyond right underneath this peak, it will slow down a lot and then go back So basically, we can here see that when I is small, your frequency of firing becomes very small, because to rise, it takes a long time. Okay, so in fact, if it is almost, if it is just touching, it'll take forever. It'll just stop, right? But if it is just barely touching, it takes a very long time to reach. And this flattened portion that you are seeing here, where it is not, it is varying very slowly. V is varying very slowly, is the point where you are just crawling under this peak. Okay, so you can see that I controls even the frequency of firing. Okay, so increased I, higher I means higher frequency. You can solve all this theoretically because it's just a quadratic nonlinearity. And when you just have to integrate that, you get some kind of a tanh function. So this is a very nice model. You can show a lot of behaviors even with this simple quadratic nonlinearity. Okay, then let us look at what is called a leaky integrate and fire neuron. So here it is similar to the previous case only, but instead of V square, you have V, right? And that you can even describe in terms of a physical realization, in terms of a circuit realization. So imagine an RC circuit where you have an external current I, right? And the capacitor charge, right, is thought to be reset whenever V crosses some VTH, or we use notation theta here. Whenever V crosses some theta, V is reset to 0. Okay, imagine that is happening. So let us see how the behavior of such a system looks. But what does it look like? So C dV by dt plus plus V by R is equal to Ix. Okay, and we multiply by R on both sides. RC dV by dt is equal to minus V plus RIX. Okay, so let us assume that Ix is equal to I naught times ut, where ut is a step function. So what is, so I'll call this RC, I'll call this tau. What is solution for this? Right, you might have learned in your electrical circuit theory course, which is simply R I naught times 1 minus e power minus e by tau. Okay, you can differentiate it and plug it back in here, and you can check that it's correct. so, so basically V increases right like this and reaches this kind of a maximum value, which is Ri naught. Now what we do is, we won't let it go until at Ri naught. You just reset it moment it reaches some threshold value of theta. So what happens is, once it reaches theta, it gets reset and gets charged up again. Once it reaches theta, it gets reset. Sorry, it gets charged up again. So this is the kind of behavior this system shows. Now, where is the spiking in this? I mean, there's no explicit spiking, but what you have to imagine in this case, you just assume that, I hope you can see this bottom line. You just assume that whenever this resetting happens, the neuron model is emitting a pulse. Okay, and this is like a action potential. It's just it's just a notional thing, right? Basically, the resetting, whenever resetting is happening, you just imagine that there is a pulse. So in that sense, it is producing a series of spikes, but which are just implied. They are not actually there. Okay, so now what is the frequency of this spiking? We can easily calculate that. So this is the expression for voltage variation. V is equal to Ri naught into 1 minus exponential minus t by tau. And when V is, and this value is equal to theta, right? That's when you reset. Okay, so basically we are trying to find the time taken to reset. So this is the theta value. The time taken to reset is, if I take it as t, using that, that's your time period of oscillation. Okay. So you solve, that is here t is you replace by small, capital T, which is like a time period. You solve that and you get this. And you can see that t is real, and it's meaningful only when r I naught is greater than theta. Okay. So that means only when I naught is greater than theta by r, right? You have firing. Otherwise, no. So what happens, right? So there is a kind of a threshold here also, and so this is time period. 1 by that gives you the frequency. So what happens here is, so only when I is greater than some threshold value, we have firing. Otherwise, there's no firing. So this is like 0, and after that there is firing, and this increases. So this is like a frequency is like 1 by log function. Okay. Yeah. So frequency is like a 1 by log function, and but only thing is, so since it is, but it keeps on blowing up. So to make it finite, and because if you look at Torsionowski model, the frequency doesn't blow up as increased current. It just saturates. And in fact, beyond the current value, it doesn't even, you don't even call it spiking. So it just kind of the plot abruptly stops beyond some current value. But to get some kind of a saturating effect where the frequency is like saturating function of the input current, what people have done is they introduce something called a refractory period, or Tref. Okay, so this is called refractory period. What that means is once a neuron spikes, it cannot get charged up until after some time. Okay, so the real neurons show this kind of behavior. So based on that, they added this constant value. So it will start charging up only after this. There's a small delay. So because of this, you cannot decrease this, the spike to spike interval indefinitely. It cannot go to 0, right? The minimum value it can go to is, so this is the T ref. So that puts a cap on the firing rate. So therefore, the previous uh, time period T, you have to add T ref to that, and frequency becomes 1 by this whole thing. So because of this, you have a kind of saturating curve, right? Frequency dependence on I naught is a saturating curve. Okay, so that is an integrated fire neuron model. These are very effective. You can construct networks of these neurons and do lots of interesting things. Right? Now let us go to the next one. So we'll take very similar thing, but but we'll look at a neuron model which doesn't have a resetting step. So here you just have only one variable, right? So that is u. So the dynamics is tau into u dot is equal to minus u plus capital V, where capital V is tan h of lambda u plus I. Okay, so so this neuron can show very interesting behaviors. The neurons that models that we have seen so far are capable of producing oscillations, and these oscillations we are calling them action potentials. So here again we have seen two kinds of models. If you look at Fujinogumo, Morris-Takar and all that, they produce limit cycle oscillations. They are smooth oscillations. Whereas if you look at the models we have seen in this class before, they produce spikes. They are not limit cycles because they have a hard resetting step, right? And so they are producing spikes and not not limit cycles. So basically, mathematically, we are trying to represent an action potential in two forms. One is using limit cycles, as we did in case of Morris-Takar and Fujinogumo and all that, or in terms of sharp spikes, which involve a hard resetting. But in this, the model we are going to talk about now, or maybe we'll continue this in the next class, right? We won't have oscillation, we won't have spikes. This neuron can simply live in two states, right? It's a binary neuron. It can live in a high state or a low state. Okay, high state you can call it like 1, or low state you can call it 0, or high state you can call it +1, and low state you can call it -1. But basically there are no oscillations here. it just can remain in a higher or low state. So these kinds of neuron models are called rate-coded neurons, which don't explicitly produce spikes. They show their output is just a scalar value, which can be in a high value or a low value. Okay. So maybe I'll continue this in next class. There are a couple of neuron models of this kind, rate-coded neurons, and we'll discuss it in next class. Thank you.